Welcome to solverfy.
So we have a spherical shell of inner radius r1 and outer radius r0, and its charge density varies with r as rho naught r1 by r. So we want to find out the field inside, in the shell, and outside. So let's start with inside. We'll consider a Gaussian surface, a spherical Gaussian surface, but obviously the charge enclosed is 0, which means the charge, the electric field is also 0, because the electric field is charge enclosed divided by 4 pi epsilon naught r squared. Part B, just a reminder again, when there is a spherical charge distribution of charge q, then it, for any point outside the charge distribution, it acts as if the charge has been concentrated at its center and is of the same magnitude. Hence, we simply can apply the point charge formula of q by 4 pi epsilon naught r squared. That is what we are doing in this case. Now, inside the sphere, we'll draw a spherical Gaussian surface. The radius will obviously be r. So the charge enclosed will be an integral because the charge density changes. So we have rho of r dv starting from r1 to r. Now this will be limits r1 to r. Rho of r is rho naught r1 by r, and the volume will be 4 pi r square. 4 pi r square dr. Now, because there is another r over here, we can change our dummy variable into, let's say, x. 4 pi x square dx, or you can call this r dash or anything you want. It doesn't matter. Now, we can cancel one of the x's, and we can pull rho naught r1 outside along with 4 pi. We have 4 pi rho naught r1 integral from r1 to r x dx. So this, because integral x dx is x squared by 2, we have 2 pi rho naught r1 r square minus r1 square. So the electric field is simply divided by 4 pi r square epsilon naught. So that's 2 pi rho naught r1 r square minus r1 square, as in the previous thing we found, divided by 4 pi epsilon naught r square. So that is, we can cancel a few more things, giving us rho naught r1 r square minus r1 square by 2 epsilon naught r square. Now for part B, once you are completely outside both the cylinders, all the complete charge enclosed will be the total charge in the spherical shell. So we simply need to find the entire charge of the spherical shell. That will be integral rho dv with limits r1 to r0. So that is integral rho naught r1 by r 4 pi r square dr, but limits from r1 to r2. Again, I'll make our dummy variable x, and I'll cancel one of the x's off. And this gives us, just like the last time, 2 pi rho naught r1 into r0 squared minus r1 squared. Instead of r, you have r0. That's it. So the electric field will be q enclosed divided by 4 pi epsilon naught r squared. So that is 2 pi rho naught r1 into r0 square minus r1 square divided by 4 pi epsilon naught r square, which is rho naught r1 into r0 square minus r1 square by 2 epsilon naught r square. So for part D, I can't upload my plotted file here, of course, but you can use any plotting software and substitute this piecewise function. What you can actually do is consider the constants. For example, rho naught r1 by 2 epsilon naught as some k, and it will simplify it much better. And your final graph should look something like this. It is 0, the field, we are plotting the field E versus R. So at R is equal to R naught, until R is equal to R naught, your field must be 0. Of course, you have not been given R1, so you can simply choose R1 to be 2 R naught. That is good enough. And the graph then goes up, because the field here is of the form 1 minus 1 by R square. And once it hits R1 again, it falls off as 1 by R square. So your shape should be something like this. And that's it.